Across the golden plains of the African savanna, where sunlight flickers across swaying grasses and acacia shadows stretch long across the earth, the zebra moves as part of a larger rhythm, a rhythm dictated by hunger, vigilance, and the ever-present threat of teeth. At first glance, a zebra's most striking feature seems almost artistic, the stark black and white stripes that ripple across its body. But this pattern, far from ornamental, serves as a frontline defense in a landscape dominated by predators with a singular evolutionary mission: to isolate, to chase, and to kill. To understand the zebra's survival, one must view its life not as a solitary experience, but as an ongoing performance within the herd. The stripes, vertical along the neck and torso, slanted over the rump, and horizontal on the legs, act not just as a camouflage mechanism, but as a dynamic visual tool. When a group of zebras moves together, especially during flight, their stripes blur into a shifting, pulsating mass. For a lion, which relies more on motion detection and contrast than color perception, the result is visual confusion. Targets appear to merge, outlines dissolve, and for a brief but critical moment, the predator struggles to isolate a single individual. In that hesitation lies survival. Recent studies using high-speed cameras and predator eye simulations have revealed that this optical illusion is more than speculation. The dazzle effect, a term borrowed from World War I naval camouflage, is a real phenomenon, disrupting a predator's depth perception and timing. Lions and hyenas, whose ambush tactics depend on surprise and precision, are forced into an error-prone decision-making process when confronted with a galloping herd of zebras. The moment of uncertainty can make the difference between a successful takedown and an exhausting, energy-wasting chase. But visual deception is only the beginning. Zebras also possess a panoramic field of vision, nearly 340 degrees without moving their heads, due to the lateral placement of their eyes. This wide-angle awareness allows them to constantly scan for movement, detecting predators long before danger closes the gap. While their acute sense of sight is a primary defense, zebras are also equipped with sharp hearing and a refined sense of smell, giving them a multi-sensory toolkit for early detection and escape. Physiologically, zebras are built for flight, not fight. Though not as fast as a cheetah in a sprint, they are capable of maintaining speeds up to 65 kilometers per hour and can sustain bursts long enough to outlast most short-range attackers. Their powerful legs, however, are not just for running. When cornered, a zebra's kick is formidable, strong enough to shatter the jaw or ribs of a lion. Some encounters caught on rare footage have shown zebras fighting back with such explosive force that entire lionesses are thrown off balance, injured, or even fatally wounded. Within the herd, survival is deeply communal. Social bonds are tight, often formed through grooming, vocal communication, and spatial proximity. Stallions patrol the edges, positioning themselves between danger and the more vulnerable females and foals. Mothers remain fiercely protective, placing their young at the center of the herd. In moments of panic, the herd moves as a single organism, not only increasing the effectiveness of their striped camouflage, but also reducing the odds that any one member will be caught. Thermoregulation, though less visible, plays an indirect role in survival. Research suggests that the black and white stripes may create tiny convection currents along the zebra's body, helping to cool the animal in the extreme heat of the savanna. A cooler body means less time spent panting or resting in vulnerable positions, and more stamina during long flights from predators. In essence, even their coat's microclimate manipulation contributes to their evasive edge. Despite their adaptations, zebras live in constant tension. Unlike many other prey species, they do not hide or burrow or roam under the cover of night. They are out in the open, day and night, grazing in exposed habitats that make them perennial targets. Yet their very visibility, paradoxically, becomes a part of their protection. In areas of tall grass, lions have the advantage, able to slink unseen toward their prey. But in open plains, zebras' early detection and group cohesion reverse the power dynamic. A lion can sprint, but only once, and a missed opportunity often means waiting another full day or more before trying again. Zebras also migrate in massive numbers, sometimes in the hundreds of thousands, crossing rivers and predator zones in search of greener pastures. During these perilous journeys, the dazzle defense becomes amplified. From the air, satellite images show undulating waves of stripes in motion. For crocodiles lurking in the shallows, This moving black and white distortion may confuse depth perception as zebras cross turbulent waters. It's not just land predators that are outwitted. Nature's predators in every form must contend with a prey animal whose evolutionary path has embraced the art of deception as an everyday survival tool. Importantly, this strategy is not static. Young zebras are born with brown stripes that darken over time, and foals must learn the herd's movement patterns, escape cues, and warning calls. They imprint on their mothers, staying close in the early months when their chances of being picked off are highest. It's during these early years that the most important survival behaviors are formed, not just running and kicking, but recognizing when to freeze, when to move with the herd, and when to disappear into the optical current. The zebra is a study in the power of evolutionary innovation. Without horns, fangs, venom, or armor, it has nonetheless become one of the savanna's most persistent survivors. It is not just fast, it is organized. It is not just visible, it is deceptive. And it is not just a grazing herbivore, it is a living illusion, a biological puzzle that predators have been trying to solve for millions of years, often with fatal miscalculations. In a land where everything visible can become a target, the zebra thrives not by hiding, but by making the act of choosing it as a target maddeningly difficult. The predator must see clearly to strike accurately, and the zebra, ever alert, ever moving, ensures that vision is the very first thing to fail. Beneath the boundless expanse of the African sky, where thorn bushes and golden grasses paint a living mosaic across the landscape, the impala lives in the constant flux between abundance and scarcity, vigilance and motion. The savanna is not merely a field of open grass, it is a tapestry of shifting resources, unpredictable weather, and perpetual risk. Here, the impala stands as the very embodiment of adaptability, its entire existence balanced on a knife's edge between predation and opportunity. As the dry season scorches the earth and the wet season breathes it back to life, the impala survives not by specialization, but through a remarkable capacity for change, demonstrating that in the African ecosystem, it is not the strongest or even the fastest that endure, but the most flexible. At dawn, the world awakens in a gentle chorus, doves calling from the acacia canopy, insects humming in the fresh dew, the air thick with anticipation. Impalas emerge from the safety of their clustered groups, their sleek, reddish-brown coats blending with the muted palette of dried grasses. To the untrained eye, they seem almost fragile, delicate limbs, large, dark eyes, twitching ears. Yet every feature has been finely sculpted by evolutionary pressure. Their limbs are not merely for running, but for leaping. Powerful tendons and muscles, anchored to lightweight bones, allow the impala to launch itself more than 10 meters in a single effortless bound. This ability to soar over shrubs, small trees, and even other impalas is not just a spectacle of grace, but a necessity for survival, as predators like cheetahs, leopards, and lions rely on speed and ambush to bring down their prey. Yet the impala's athleticism is only the surface of its adaptive genius. It is in its feeding habits that its true strategy unfolds. The impala is a mixed feeder, one of the few savanna antelopes equally skilled at grazing on grasses and browsing on leaves, shoots, and herbs. This dietary flexibility means that as grass withers under the dry season's heat and other grazers struggle to find food, the impala shifts its focus to the tender leaves of shrubs and low-hanging branches. The structure of their lower jaw and specialized teeth allow for this seamless transition, letting them process both tough grasses and softer browse. In wet seasons, when grass is plentiful and lush, impalas blend into herds scattered across the open plains. During the harsh months, they cluster in denser woodland, picking through foliage where few competitors can follow. This dynamic foraging pattern not only buffers them against food shortages, but also minimizes overlap with other herbivores, reducing direct competition. Predation, however, is an ever-present force that shapes every behavior. Impalas possess acute senses. Eyes set high and wide on the skull provide nearly panoramic vision, while their large, mobile ears scan constantly for the faintest rustle of danger. A single alarm snort from a vigilant female can trigger a wave of movement as the herd erupts into a coordinated, chaotic flight. Here, the impala's signature leap, known as stotting or pronking, becomes more than just evasion. It is a calculated display of fitness, signaling to would-be predators that pursuit is unlikely to end in success. These high, twisting jumps serve both to confuse an attacker and to broadcast the impala's health and agility. Predators, ever attuned to efficiency, often abandon the chase when confronted with such displays. Survival for impalas is not an individual endeavor, but a collective one. Herd structure shifts fluidly in response to environmental pressures. During the breeding season, dominant males establish temporary territories, corralling females and fending off rivals in a flurry of chases, clashes, and vocalizations. Outside of the rut, impalas coalesce into mixed herds, males, females, and juveniles mingling in groups that can number in the hundreds. This social organization is not merely for reproduction or companionship, but a living defense system. With so many eyes and ears, the likelihood of detecting a stealthy predator increases dramatically, and the confusion of mass movement reduces the odds that any one individual will be targeted. Moreover, impalas demonstrate a fascinating social flexibility. When conditions change or resources dwindle, herds can split and reform as needed, tracking food and water across shifting ranges. Water, the lifeblood of the savanna, governs much of the impala's seasonal rhythm. As ephemeral pools evaporate and permanent rivers recede, impalas embark on subtle migrations, moving in tune with the cycles of rain and drought. Their need for water is acute. Unlike some antelopes that can subsist on dew or dry forage alone, impalas must drink regularly, drawing them to waterholes that become both life-giving oases and death traps. Here, the complexity of the ecosystem becomes starkly visible. Crocodiles lurk in the shallows, lions and leopards lie in ambush at the edges, and the very act of drinking becomes a tense negotiation between necessity and risk. Impalas approach cautiously, often in groups, with some drinking while others keep constant watch. The interplay of alertness and vulnerability at these waterholes exemplifies the impala's finely tuned balance between opportunity and danger. Less visible but equally crucial are the physiological adaptations that allow impalas to endure the savanna's extremes. Their coats shift with the seasons, growing thicker in the cool, dry months and sleeker when the rains return. Beneath the skin, a complex network of sweat glands and capillaries enables efficient thermoregulation, allowing them to remain active during the hottest parts of the day when predators are often resting. This capacity to withstand heat without sacrificing alertness or stamina confers yet another survival advantage, enabling impalas to graze or browse during times when risk is temporarily reduced. The impala's reproductive strategy further underscores its adaptability. Females typically synchronize births to coincide with the onset of the rains, when grass is most abundant and the nutritional demands of lactation can be met. This phenomenon, known as birth synchrony, creates a glut of vulnerable young, briefly overwhelming predators and increasing the odds of individual survival. Newborn impalas, mere minutes after birth, are already on their feet, blending into the landscape as their mothers usher them into the protective anonymity of the herd. Rapid growth and early mobility are essential. In the savanna, laggards are swiftly claimed by lions, hyenas, or wild dogs. Symbiotic relationships and ecological roles further illustrate the impala's importance within the ecosystem. As both grazers and browsers, impalas influence plant communities, preventing overgrowth of certain species and promoting biodiversity. Their dung, rich in partially digested seeds, helps disperse a wide variety of plants, supporting regeneration after the rains. Impalas also host oxpecker birds, which feed on ticks and parasites, benefiting both species in a classic example of mutualism. Yet for all their adaptability, impalas remain deeply vulnerable to the ecological upheavals of drought, habitat fragmentation, and human encroachment. Their survival strategies, honed over millennia, now face pressures beyond the reach of instinct and behavior. In the broader web of the savanna, the impala is not merely prey, nor simply a grazer among many. It is a keystone of resilience, a species whose very existence is a testament to the power of flexibility in the face of constant uncertainty. Every leap across the grassland, every silent pause beneath the thorn bush, every shift in diet or movement across the landscape is an adaptation carved by necessity, shaped by the twin forces of predation and opportunity. In the endless competition between teeth and hoof, hunger and evasion, it is the impala's gift for adaptation, its double life as both grazer and browser, sprinter and leaper, sentinel and social strategist, that ensures its survival against the odds. The savanna is a place of unforgiving selection, but for the impala, it is also a stage for innovation, where survival is not just a matter of speed or strength, but of learning, adaptation, and the endless dance with a world in flux. In the early hours before sunrise, When the air still carries the vestiges of night's chill and the savanna is suspended in the hush of pre-dawn, a new day reveals the unmistakable silhouettes of giraffes rising above the mosaic of trees. Their long necks and legs, seemingly exaggerated by nature's hand, grant them dominion over a vertical realm that few other animals can reach. The sun's first rays illuminate a shifting forest of acacia and combretum, but always above the canopy, the giraffe surveys its world, a living watchtower, casting its gaze over kilometers of grassland from a vantage point few predators can challenge. This height is more than a quirk of evolution, it is an adaptation of profound ecological consequence. At over 5 meters tall, a giraffe's field of vision sweeps uninterrupted across the landscape, allowing it to spot the subtle approach of danger long before ground-dwelling prey could sense it. The placement of the giraffe's enormous forward-facing eyes, positioned to take in a near panoramic view, gives these animals an unrivaled early warning system. When a pride of lions begins its low, calculated stalk through the golden grass, giraffes are often the first to see the threat, their heads pivoting and ears swiveling to triangulate the movement. This vigilance does not only benefit the giraffe. As their behavior changes, other herbivores, zebra, impala, wildebeest, take heed, reading the tension in the giant's body language and often reacting to danger before they themselves are aware of its presence. But the giraffe's height serves an equally vital role in the relentless competition for food. In a biome where the dry season can turn the landscape brittle and brown, access to greenery becomes a matter of survival. While smaller browsers and grazers scour the ground for what remains, the giraffe's elongated neck and prehensile tongue, stretching up to half a meter, granted exclusive access to the most nutritious leaves at the very tops of thorny acacia trees. This not only provides sustenance when other sources run out, but also shapes the very structure of the savanna itself. Giraffes are ecosystem engineers. Their selective feeding prunes trees, encourages regrowth, and shapes plant communities in ways that ripple through the food web. The relationship between the giraffe and the acacia is complex and dynamic. Acacias, in response to repeated browsing, have evolved formidable thorns, and even the ability to release chemicals into the air when grazed upon, warning neighboring trees to increase their own chemical defenses. Yet giraffes, undeterred by thorns, employ a thick, toughened tongue and lips, and a specialized saliva that neutralizes many of these plant toxins, revealing the ongoing evolutionary arms race between herbivore and plant. Despite their lofty stature, giraffes are not immune to predation. Lions, ever opportunistic, pose the greatest threat, particularly to calves or occasionally to adults in rare, desperate hunts. When danger does close in, the giraffe's defense is as extraordinary as its height. The muscles and ligaments of the hind legs are engineered for explosive power, delivering a kick with enough force to break bones or rupture internal organs. There are recorded instances where a single, well-placed kick has shattered the skull or jaw of an attacking lion. This capacity for lethal defense, combined with vigilance and group cohesion, ensures that adult giraffes are among the most challenging prey on the savanna, hunted only by the boldest or hungriest of predators. The giraffe's towering anatomy also presents unique physiological challenges, which evolution has solved with elegant precision. A heart weighing over 10 kilograms beats beneath a chest as deep as a barrel, generating immense pressure to push blood up the long neck and into the brain, twice the average arterial pressure of a large mammal. Valves in the neck veins prevent blood from rushing to the head when the giraffe lowers its neck to drink, protecting against fainting and stroke. To drink, a giraffe must splay its legs awkwardly, exposing itself to attack. It is in these moments, when the animal is forced to lower its head below its heart, that the intricate system of blood vessels and valves becomes essential, allowing the giraffe to recover quickly and remain vigilant, even in this vulnerable position. Social structure among giraffes is fluid, with individuals forming loose, non-territorial groups that shift and merge over time. These aggregations, known as towers, are rarely rigid family units, but rather temporary gatherings based on food availability, reproductive status, and protection. Calves are often left in nurseries, watched over by 1 or 2 adults while others forage nearby. This communal vigilance enhances survival, for while a single giraffe may be an imposing sentinel, a group commands a network of overlapping sightlines, increasing the odds that danger will be detected before it strikes. The young, though well camouflaged with a more irregular coat pattern and spending much of their time hidden in the undergrowth, remain vulnerable to predation by lions, hyenas, and leopards. Mortality is high in the first months of life, but those that survive benefit from the protective presence and lessons of the adults. The giraffe's daily life unfolds at a deliberate pace. Despite their size, they move with surprising grace, crossing great distances in search of scattered food sources and water, their heads nodding with each rolling stride. This constant movement is a necessity in the nutrient-poor soils of the savanna, where resources are patchy and competition is fierce. Giraffes have relatively low fat reserves, relying on continuous foraging to meet their high metabolic demands. Their digestive system is complex, with a 4-chambered stomach like that of cattle, allowing them to efficiently process the tough, fibrous leaves that constitute their primary diet. Through this rumination process, they extract the maximum possible nutrition from the scarce, sun-baked foliage. Interactions with other species further define the giraffe's role in the savanna ecosystem. Oxpeckers perch atop their backs and necks, picking off ticks and parasites in a mutualistic relationship that benefits both bird and mammal. The presence of giraffes in an area often attracts other herbivores who associate their calm demeanor with safety and exploit their vigilance as an early warning system. Even predators learn to use the giraffe's reactions as cues, moving in tandem with their gaze to locate herds of potential prey. Seasonal cycles shape every aspect of giraffe behavior. In the dry months, they travel greater distances to find food and water, enduring heat and scarcity with stoic resilience. When the rains return, the savanna erupts in a flush of green, and giraffes follow the abundance, sometimes forming larger groups at the edge of newly flooded grasslands. Breeding peaks with resource availability, and after a gestation period of nearly 15 months, females give birth standing up, the newborn calf dropping 2 meters to the ground in its first abrupt lesson of life. Within hours, the calf stands and moves, already attuned to the dangers of a world where visibility is both a blessing and a curse. Despite their many adaptations, giraffes face threats beyond those of natural predation. Habitat loss, human encroachment, and illegal hunting have driven down populations in many regions, leading to their classification as vulnerable by the International Union for Conservation of Nature. Their ability to shape the ecosystem and serve as sentinels is increasingly tested by shrinking ranges and fragmented habitats, making their continued survival a matter not just of evolutionary fitness, but of urgent conservation. Yet in the dawn light of the African plains, the giraffe still stands as a testament to nature's ingenuity. A creature whose every feature, from elongated neck to specialized heart, serves a precise function in the complex, ever-changing dynamics of the savanna. To observe a giraffe is to witness the convergence of biology, ecology, and adaptation in a form both improbable and perfectly suited to its environment. Through its height, it commands the high ground of survival, translating a singular physical trait into an entire way of life, and in doing so, shapes not only its own destiny, but the fate of the ecosystem it surveys. In the parched clay and scattered shrubs of the African savanna, where the sun beats down with unrelenting intensity and the horizon shimmers in heat haze, the warthog moves with a purposeful swagger that belies its reputation as a ragged scavenger. At first glance, its sparse bristled mane, protruding tusks, and wart-like facial protuberances suggest a creature of little finesse. Yet beneath this rough exterior lies an expert strategist of survival, one whose every behavioral and anatomical trait has been honed by the twin forces of predation and environmental extremes. As dawn breaks, warthogs emerge from the safety of their chosen burrows, often abandoned aardvark or porcupine dens, that they reverse into with the remarkable precision of a seasoned driver backing into a garage, positioning their formidable tusks and hardened facial bosses at the entrance. In this inverted posture, they stake out a defensive choke point. Tusks forward, they block the tunnel against lion, hyena, and leopard, turning their sleeping quarters into an armored fortress. The selection of burrow is no random act. Warthogs show remarkable spatial memory and an acute sense of topography, choosing sites with entrances low enough to force attackers into a bottleneck, yet high enough to allow rapid exit. Beyond defense, these burrows provide a crucial microclimate. Some 8 to 12 degrees cooler than the savanna's midday heat, they offer respite from the relentless sun and reduce water loss through evaporative cooling, a vital adaptation for an ungulate with thin skin and sparse fur that would otherwise scorch under direct rays. When an alarm snort or distant rustle penetrates the early morning calm, Warthogs abandon the battlements of their tunnels in a blur of speed and agility, their tails held upright like semaphore flags that signal danger to the dozen or more family members gathered outside. This tail-up posture is both a communication device and an aerodynamic rudder, aligning the group's flight path as they bolt across the uneven terrain. Remarkably, warthogs can sprint at speeds approaching 55 kilometers per hour, weaving through thorny scrub and leaping over termite mounds with an agility that confounds predators expecting a lumbering brute. Their gait is a bounding trot punctuated by galloping bursts, optimized by strong shoulder muscles and spring-like tendons that store and release energy with each bound. This unpredictable zigzag pattern not only increases the energy cost to the chasing predator, but also exploits the warthog's low center of gravity. When pursued, a lion trained on broad plains may misjudge its turning radius, losing precious seconds that can make the difference between life and death. Yet flight is only part of the warthog's defensive repertoire. When cornered at the edge of a waterhole or backed against a thorn thicket, the warthog will wheel on its pursuer, bristling mane erect and heavy tusks, slashing in wide arcs that can lacerate hide, puncture lungs, or sever tendons. These tusks, curved, ivory-white upper canines and smaller lower canines, grow continuously, their tips worn to razor edges through gnawing on roots and bark. Beneath the skin, powerful jaw muscles anchored to robust zygomatic arches deliver a crushing bite, enabling the warthog to root through hard-packed earth in search of tubers and bulbs, and to defend itself with the same force it uses to excavate its daily forage. The facial warts, in fact thickened dermal pads, cushion the impact of tusk thrusts when males clash in ritual combat during the mating season, absorbing shock and protecting vital structures. Interestingly, this combative behavior is rarely fatal. Instead, it establishes social hierarchies and breeding rights through ritualized sparring, demonstrating how an adaptation useful in intraspecific competition can double as an anti-predator weapon. Socially, warthogs live in small family groups called sounders, typically comprising a dominant female, her offspring, and juvenile female relatives, while adult males often range alone or in bachelor groups. This loose structure reflects a balance between cooperative vigilance and resource competition. Sounders forage together across a mosaic of grassland and woodland, their communal snuffling and grunting, not only locating food, but also creating a network of auditory cues that keep the group synchronized. When one member detects a predator, the entire sounder responds within seconds. Grunts become shriller alarm calls, tails rise, and the group cascades toward the nearest burrow. Juveniles learn these cues early, imitating the rapid tail raises of their elders and practicing sprints through the thorn bush under the watchful eye of protective females. The warthog's diet is similarly opportunistic, ranging from grasses and roots to fallen fruit, carrion, and insect larvae, a flexibility that buffers against seasonal scarcity. During the wet season, when grasses provide sufficient moisture, warthogs may abstain from drinking for weeks. In the dry season, they risk predator-laden waterholes to quench their thirst, timing their visits at dawn or dusk when the UV index is lower and aerial predators like martial eagles pose less of a threat. Thermoregulation plays a subtle but critical role in warthog behavior. Their sparse coat and large bare ears facilitate heat dissipation, while the burrow's stable temperature allows for extended periods of rest without water loss. On the hottest afternoons, warthogs may wallow in shallow mud, using the cooling, moisture-retaining properties of the clay not only to lower body temperature, but also to deter ectoparasites. As the mud dries, it forms a protective crust that the animal rubs against rough surfaces, shedding ticks and lice in the process. This simple behavior exemplifies the warthog's integration of environmental features into its survival repertoire, transforming the landscape's resources into tools for defense and hygiene. In quieter moments, when the sun dips below the horizon and predators retreat to the shade of baobabs and fig trees, warthogs emerge cautiously from their refuges to graze on the tender overnight shoots. The nocturnal forays are governed by a sophisticated risk-reward calculus. With reduced visibility, the warthogs rely on their keen sense of smell and heart rate synchronized sniffing to detect lurking hyenas or leopards. Their eyes have a higher proportion of rod cells than other ungulates, enhancing low-light vision but sacrificing color discrimination. An evolutionary trade-off that favors predator detection over nuanced color perception in dim conditions. As dawn approaches, they slip back into the safety of their chosen burrows, tusks and warts, once again turned to face the world's dangers, ready to repeat the cycle of defense, foraging and escape that has defined their existence for millions of years. Thus, in the warthog's uneasy alliance with aardvark and porcupine burrows, in its lightning-fast sprints and zigzag flights, and in the lethal promise of its tusk-armed charge, we glimpse an animal forged by the crucible of savanna survival. It is a creature that has turned vulnerability into advantage, harnessed the land's features as extensions of its own body, and developed a suite of behaviors and adaptations that transform even the most abandoned burrow into a bastion of safety. In the warthog's world, life and death balance on the edge of a tusk, the rim of a burrow, and the perfect timing of a flight that can outpace the fastest hunters on Earth. With the break of the wet season, an ancient pulse begins to thrum through the heart of the Serengeti, a ripple that swells into a rolling thunder as hundreds of thousands of wildebeest hooves strike the parched earth in unison. This is no haphazard parade, but a meticulously orchestrated exodus born of evolutionary necessity, a cyclical gamble where the prize is fresh pasture and the cost is measured in risk and sacrifice. As dawn's pale light spills over the horizon, the first long columns of gaunt, grey-brown bodies materialize from the tall grasses, each animal guided by an instinct as old as the plains themselves. To stand still is to invite starvation. To move is to challenge crocodile-filled rivers, pride-dominated territories, and the ever-watchful eyes of lions, hyenas, and other predators that see the migrating mass as an all-you-can-eat buffet. From the air, the migration appears as a living river, its banks formed by the ragged edges of zebra and gazelle herds, intermingling with the wildebeest's darker tide. Yet it is a journey fraught with peril from the outset. As the lead animals crest a ridge, they pause, heads raised, nostrils flaring, sampling the wind for scents of danger and the faint promise of rain-dampened grass beyond. This pause is far from idle. It is a moment of collective decision-making, a herd-level appraisal of the route ahead. For wildebeest, navigation is a symphony of sensory inputs, olfactory memories of past migrations stored in neural pathways, the direction of prevailing winds carrying the scent of new growth, the subtle shift of vegetation patterns seen from their elevated vantage. These cues guide them toward the short-lived grass flush that follows seasonal rains, even when the rains falter or shift location, demanding real-time adjustments in heading and pace. As the herd descends into the valley where the Mara River winds like a silver ribbon, the first true test of their gamble emerges. Along its banks, crocodiles lie submerged, ancient reptiles with jaws capable of exerting more than 16,000 newtons of force, enough to crush bone with a single snap. In this crucible, the wildebeest's physical and behavioral adaptations meld in desperate harmony. Their hooves, sturdy and crescent-shaped, provide grip on slippery riverbanks, and their tight, compact limbs enable rapid acceleration into bounding leaps. Rhythmic groups of animals surge forward, bodies pressed together in a living mass that reduces the odds any one individual will be grabbed. Those caught in the jaws of the Nile crocodile often become grotesque spectacles, trailing behind the herd as both dire warnings and grim beacons. Yet the vast majority make it across, propelled by collective momentum and sheer numbers. Survival here is a probabilistic affair. A recent study tracking crossing events recorded mortality rates at certain bottlenecks topping 15%, but the migration scale ensures that even with such losses, the species thrives. The wildebeest's digestive physiology plays a subtle role in this endurance. As foregut fermenters, they can extract nutrients from low-quality forage with astonishing efficiency, thanks to a multi-chambered stomach and symbiotic microbes that break down cellulose into volatile fatty acids. This allows them to subsist during the long transit on marginal grass, preserving energy for the strenuous river crossings and the predator-dominated plains that follow. Their rumination process, a slow, deliberate regurgitation and rechewing of partially digested food, often continues on the move, a testament to the seamless integration of feeding and migration. Reaching the far bank does not mark the end of danger. The Mara's opposite shore is an open expanse where lions lie in wait, stalking the exhausted or young and old members of the herd. Here, the wildebeest strategy shifts from mass crossing to rapid dispersal. In these moments, individual agility and alertness become paramount. Adult wildebeest remain vigilant even as they bound away, coordinating alarm calls and erratic flight patterns that force predators to constantly recalibrate their ambush tactics. The landscape itself shapes these interactions. Scattered termite mounds become impromptu watchtowers, offering vantage points to survey for lingering threats, while fallen trees and thickets provide brief respite for the wounded to slip away from pursuers. The central Serengeti's grassy plains are not the only danger zone. In the western corridor, herds follow a looping path that skirts volcanic highlands, where cooler microclimates delay grass growth and force the animals into narrower corridors.
Here, the wildebeest adjust their pace, timing their arrival to coincide with the greening of the volcanic soil, and their physiology responds in kind. Thyroid hormone levels shift to increase metabolic rates, enhancing muscle endurance for the final leg of their journey.
As the rains complete their circle, the wildebeest swell once more, congregating in vast calving grounds where weakness is disguised by the sheer number of newborns. This reproductive timing, birth synchrony, overwhelms predators with too many targets at once, ensuring that a substantial portion of calves survives to adulthood. Within hours of birth, calves can stand, find milk, and run alongside their mothers. This rapid development is critical in a world where a moment's delay can mean becoming a lion's meal. Yet the migrations do not occur in isolation. They are threads woven into the larger tapestry of savanna ecology. Scavengers, vultures, hyenas, jackals patrol behind the herds, poised to exploit the inevitable casualties. In doing so, they speed nutrient cycling, returning detritus to the earth and supporting the growth of the very grass that sustains the wildebeest. Even the small egret birds perched on their backs, plucking ticks and parasites, play a role, reducing disease burdens that could otherwise decimate herds during high-density gatherings. Wildebeest migrations stir the air and earth alike. Dust clouds raised by thousands of hooves alter temperature and humidity locally, creating feedback loops that can influence weather patterns and, in turn, future migrations. Understanding the wildebeest's great gamble requires acknowledging the multi-scalar nature of their journey, from the microscopic communities in their rumen to the continental climatic cycles that drive the rain. It is a narrative of trade-offs, the risk of starvation versus the risk of predation, the cost of energy spent in transit versus the nutritional payoff of fresh grazing lands. It is a tale written over millennia, preserved in genetic memory, and played out anew with each season's turn. For predators, the migration represents an opportunity to exploit weaknesses, but for the wildebeest, it is the very mechanism by which they evade a static doom, leveraging movement, timing, and sheer numbers as the ultimate survival toolkit. By the time the last columns of wildebeest file back toward the southern plains, the cycle resumes its inexorable rhythm. Grasses in their wake grow fatter, courtesy of the nutrients exchanged between soil and animal, and predators adjust their territories to follow the next wave. In this dance of life and death, the migration emerges not as a singular event, but as the defining heartbeat of an ecosystem, pulsing with vitality, loss, and regeneration. It is here in the tension between stillness, which means starvation, and motion, which brings both sustenance and danger, that the wildebeest stakes its claim on survival, proving that in the unforgiving theater of the savanna, boldness and adaptation are the truest measures of endurance. At the edge of the midday heat, where the savanna's golden grasses unfurl like an ocean under the relentless sun, a herd of Cape buffalo stands as an unyielding bulwark against the predatory forces that roam the plains. Their massive bodies, draped in dark hides streaked with mud and dust, form an imposing wall of muscle and horn, each individual locked into an instinctual pact of mutual protection. This is no loose aggregation of grazing ungulates. It is a living phalanx, honed by millennia of conflict into one of the most formidable defensive machines in the African ecosystem. To witness a buffalo herd in standoff with the stalking pride of lions is to see cooperation elevated to an art form, every twisting horn and thunderous hoofbeat telling a story of collective resilience, of an evolutionary strategy written in steel and bone. It begins with vigilance. Buffalo grazing patterns are anything but haphazard. Individuals take turns resting and feeding at the herd's periphery, eyes scanning, ears swiveling at the slightest crackle of dried grass or a distant low growl. Their wide-set eyes afford them near panoramic vision, while their muzzles, equipped with a sensitive array of vibrissae, detect subtle vibrations transmitted through the ground when a predator's paws touch down. Even the wind plays its part, carrying the scent of ambush across vast distances. Buffalo often orient themselves upwind of suspected threats, ensuring that a potential stalker cannot slip unnoticed into striking range. Within each herd,
a loose hierarchy emerges. Older, battle-hardened bulls take up positions at the front during resting and grazing periods, serving as both watchmen and shock troops, while younger calves cluster near the center, shielded by the broad backs of their protectors. Predators such as lions and hyenas have learned to respect this living citadel. Hunting a buffalo herd is not a casual undertaking. It is a tactical operation fraught with risk. Lionesses attempting to single out a calf or a weakened adult must first isolate it from the mass, a feat that requires stealth, patience, and cooperation among the hunters. Yet the herd's response to any assault is nearly instantaneous and nearly unanimous. At the first sign of aggression, a low bellow from the lead bull, the sudden spread of the herd's flank, buffalo shift from relaxed grazing to a disciplined formation. Adults at the outer edge pivot inward, horns lowered and hooves braced, creating a circular barrier around the vulnerable. The calves, their legs still unsteady in their first months, disappear into the protective huddle, while the bulls advance, heads swinging in wide arcs, ready to meet any predator that dares to press the attack. The physics of a buffalo charge are as lethal as they are spectacular. A mature bull can weigh upwards of 900 kilograms and wield horns that span nearly a meter from tip to tip. When these leviathans surge forward, the earth trembles beneath their staggering mass. Each hoofprint is a seismic drumbeat announcing their approach. Their horns, thick at the base and tapering to razor points, are used not only in intraspecific contests of dominance, but as weapons of last resort against predators. In multiple recorded incidents, buffalo have gored lions, piercing their ribs or disemboweling them with a single thrust, turning the tables on the hunters in a brutal testament to the inherent danger of targeting this species. It is this very reputation for violence that deters many predators from confronting a healthy herd, relegating their attacks to the old, the sick, or the very young. Individuals whose removal, though tragic, does little to destabilize the overall defense. Beneath the thunderous displays of force lies a subtle choreography of communication. Buffalo bellow in low-frequency calls that resonate across the plains, vibrations picked up by the sensitive auditory system of herd members even when visibility is low. These vocalizations vary in pitch and duration, conveying information about the location and urgency of a threat. A short, staccato grunt may signal a distant disturbance, prompting heads to lift and ears to pivot, while a deep, drawn-out roar triggers immediate consolidation of the herd into defensive positions. Concurrently, visual cues, raised tails, shoulder brushes, synchronized stepping, reinforce the auditory warnings, creating a multisensory network that binds the group's response into a single, cohesive movement. Ecologically, the buffalo's battle code has far-reaching implications. By denying predators easy access to their young, buffalo herds maintain population stability, ensuring that grasslands are grazed in a pattern that prevents overgrowth and encourages plant diversity. As mega herbivores, their feeding behavior shapes the very structure of the savanna, trampling dense shoots, uprooting woody saplings, and fertilizing the soil with nutrient-rich dung. These modifications foster habitats for smaller grazers and ground-nesting birds, demonstrating how the buffalo's defense strategy underpins an entire web of life. Moreover, the nutritional yield of a buffalo kill is so substantial that scavengers such as hyenas and vultures often depend on the fruits of predation when lions finally succeed in isolating an individual. Thus, even a fallen buffalo contributes to the sustenance of the wider ecosystem, perpetuating cycles of energy flow that sustain life on the plains. But the buffalo's prowess is not limited to confrontation. It extends to an astonishing display of rescue when one of their own is seized. In rare but documented events, buffalo have been seen charging into a pride of lions that has a calf in its jaws, trampling attackers and prying the victim free with horn tips. These audacious interventions depend on split-second coordination. Bulls and cows converge on the ambush site from multiple directions, creating confusion and seizing the initiative from the predators. Their objective is singular: to force enough chaos that the targeted buffalo can break free and flee. Such acts of collective heroism underscore the depth of the social bonds within the herd, forged by the recognition that any individual's vulnerability is a vulnerability shared by all. In this sense, the buffalo's battle code transcends mere self-defense. It is an ethic of mutual obligation writ large across the savanna. Thermoregulation adds another dimension to the buffalo's adaptive arsenal. Despite their massive size, Cape buffalo maintain body temperatures comparable to smaller mammals by exploiting behavioral and physiological mechanisms.
During the midday heat, herds often seek refuge in the shade of gallery forests along riverbanks, where the air temperature can be several degrees cooler and humidity higher, reducing water loss through evaporation. They submerge their heads and bodies in shallow pools, using the cooler water to dissipate heat through contact conduction. On particularly stifling days, they form tight clusters with their heads coiled against another's flank, a posture that minimizes exposed surface area to solar radiation while conserving moisture. These strategies allow them to remain active during the hottest periods, maintaining vigilance and grazing when other herbivores must rest, and thereby mitigating competition for food. Reproductive timing among Cape buffalo further exemplifies the herd's strategic resilience. Females synchronize births to coincide with the end of the dry season, when grasses begin to sprout anew under the softening sun. This birth pulse floods the ecosystem with vulnerable calves, overwhelming predators, and ensuring that a significant proportion of offspring survive. Calves, capable of standing and walking within minutes of birth, are guided to the relative safety of the herd's interior, where they nurse behind a curtain of vigilant adults. The act of calving often triggers a temporary cessation of grazing, as the herd forms a protective semicircle around the mother and newborn, minimizing exposure to hidden threats. Within days, the calves' rapid growth and integration into the herd's social fabric reinforce the buffalo's collective strength, ensuring that the next generation is raised under the aegis of the battle code. Yet, despite their martial reputation, buffalo face existential threats beyond the natural predatory cycle. Emerging diseases such as bovine tuberculosis and foot and mouth disease can sweep through herds with devastating speed, overcoming individual immune responses and overwhelming the herd's capacity for defense. Habitat fragmentation and human encroachment further undermine the battle code by disrupting migration corridors and reducing access to water and forage. As herds shrink and isolate, the density of individuals falls below the threshold needed to maintain effective communal defense, leaving them vulnerable both to predators and to the stresses of environmental change. Conservation efforts, therefore, must appreciate the buffalo's social and ecological complexity, protecting not just individual animals, but the landscapes and movement patterns that sustain their centuries-old alliance against the savanna's hazards. In the thunder of hooves, the clash of horns, and the unified roar of the herd, the Cape buffalo reveals a truth at once primal and profound. In a world governed by teeth and talons, survival often depends less on individual strength than on collective will. Each buffalo is both warrior and guardian, bound by a code that demands sacrifice and solidarity in equal measure. To study their battle code is to glimpse an evolutionary narrative written not in solitary conquest, but in communal defiance, a testament to the power of cooperation under the harshest conditions. The buffalo herd, with its armor of hide and horn, stands as a monument to the savanna's relentless drama, a living bulwark where life perseveres through unity, and where the fiercest battles are won not by the lone combatant, but by those who stand together in the face of annihilation. As the first light of dawn unfurls across the savanna, the landscape seems wrapped in a translucent veil of gold, each blade of grass and scattered termite mound rendered in crisp, humid clarity. Amid this awakening world, Thompson's gazelles gather at the edge of the plains, their slender frames poised between tension and grace. At a glance, their sandy coats and white underbellies offer a modest camouflage against the rolling grasses. But it is their remarkable aerial display, stotting, that transforms the ordinary into the extraordinary. Stotting, or pronking, is the gazelle's signature maneuver, a series of explosive, high-arched leaps that launch head, neck, and torso into the air while the legs remain rigid and extended. To witness a gazelle stot in response to a lurking predator is to see evolution's choreography at its finest, as muscle, tendon, and instinct converge in a display that redefines survival. The phenomenon begins with a predator's approach, often invisible to the prey, until the faintest disturbance reaches their senses. A solitary lioness may prowl through tall grass, her body low and motionless, the tip of a tail twitching as she inches forward. A cheetah, its spotted coat a whisper of concealment, may crouch behind a fallen baobab root, calculating the burst of speed that will decide life or death. Yet even before sight or sound confirms danger, the gazelle's acute senses have detected the threat. Their large dark eyes possess a high concentration of rod cells, optimized for detecting motion and discerning shapes in low-light conditions, while their broad ears capture the subtlest rustle. Even the ground tells its story. Vibrations from padded paws can travel through soil and reed, alerting the keen-hoofed herbivores at a distance. In the split second between detection and response, the gazelle's complex neurological circuits summon muscles to action, priming them for the leaps to come. Then comes the leap. With a sudden contraction of powerful limb muscles, a gazelle springs skyward, legs locked in extension, the body forming a rigid arch against the backdrop of the rising sun. Each stot reaches heights of up to 2 meters, a breathtaking testament to elastic energy storage in the tendons. As the fore and hind limbs compress at ground contact, energy is stored like a coiled spring, then released in an instant, propelling the animal upward. This process, governed by the principles of biomechanics, is not mere spectacle. It requires a precise ratio of tendon stiffness to muscle strength, a balance tuned by natural selection to maximize jump height while minimizing energy expenditure. The result is a leap that, in kinetic terms, communicates a message. The jumper is in peak condition, well-fed, agile, and unlikely to be caught. But why would a prey animal reveal its presence with such conspicuousness? The answer lies in the economics of predation. For a predator, each chase is a gamble of caloric investment versus potential reward. Lions, for instance, expend 1,800 kilocalories on average per successful hunt. But failures, common and costly, can burn through energy reserves critical for thermoregulation and muscle maintenance. By stotting, a gazelle conveys honest information about its fitness, effectively signaling to the predator that pursuit is unlikely to pay off. In behavioral ecology, this is known as an honest signal, and it reduces unnecessary chases, conserving energy for both parties and minimizing risk of injury or exhaustion. Predators learn from experience. A lioness that watches a stotting gazelle is more likely to abandon the hunt, redirecting her efforts toward easier targets. Over evolutionary timescales, predators avoid stotters, and stotting gazelles enjoy a higher survival rate, reinforcing the behavior's prevalence. Yet even within this straightforward model of honest signaling, stotting is layered with complexity. Gazelles do not stot indiscriminately. Rather, they assess the type and proximity of the threat to decide whether to leap or flee directly. Research has shown that when pursued by cheetahs, specialists in high-speed pursuit, gazelles often flee without stotting, opting instead for rapid zigzagging to exploit their own burst acceleration. In contrast, when confronted by ambush predators such as lions or hyenas, where stealth and prolonged stalking rather than outright speed determine success, stotting is more frequent. This context-dependent strategy demonstrates the gazelle's cognitive flexibility. They interpret predator identity and behavior, tailoring their response to maximize survival odds. Such decision-making implicates advanced neural processing, whereby sensory input is integrated with past experiences encoded in memory, yielding a behavioral choice suited to immediate threat conditions. Beyond predator deterrence, stotting serves social functions within gazelle herds. When one individual launches into the air, neighbors follow suit in rapid succession, creating a rolling wave of leaps that ripples across the group. This synchronous stotting amplifies the signal's potency, reinforcing the herd's overall fitness impression. For juveniles, participation in collective stotting serves as a training ground for both physical conditioning and social learning. Young gazelles practice smaller pronks, gradually building the muscle and tendon resilience needed for full-height leaps, while observing adult behavior to discern when stotting is appropriate. This ontogenetic development ensures that survival strategies are transmitted across generations, embedding stotting within the species' behavioral repertoire. Thermoregulation, although less obvious than aerial displays, intertwines with the stotting narrative. Gazelles, like other ungulates, face the dual challenge of dissipating body heat while maintaining readiness for rapid escape. Their adaptations include a specialized nasal cavity that cools incoming air through countercurrent heat exchange and a high density of sweat glands around their muzzle and flanks to facilitate evaporative cooling. Stotting, however, offers a transient benefit. Each leap briefly increases airflow across the body, augmenting convective heat loss. Though marginal compared to other cooling mechanisms, this auxiliary effect demonstrates how a behavior selected for anti-predator purposes can yield complementary physiological advantages. This intricate interplay of biomechanics, sensory acuity, cognition, and physiology unfolds against a backdrop of shifting ecological dynamics. Seasonal rains sweep across the plains, turning parched landscapes into verdant seas of grass that nourish both prey and predator. In the wet season, Abundant forage allows gazelles to maintain the fat reserves and muscle mass required for high-energy stotting displays. As the dry season descends, however, competition for food intensifies and the nutritional threshold for effective stotting rises. Under such stress, only the fittest individuals can afford the energy outlay, ensuring that stotting remains a reliable indicator of condition. Simultaneously, predators adjust their hunting patterns to exploit the relative weakness of undernourished prey, reinforcing the stotting fitness feedback loop that underlies survival outcomes. Occasionally, rare behaviors emerge that shed new light on stotting's ecological role. Observations in certain high-predation areas have documented gazelles combining stotting with group drifting, a lateral movement away from the threat that maintains visual contact while increasing distance. This composite tactic suggests that stotting can serve not only as deterrence, but as a means of coordinating collective retreat, using the visual spectacle of synchronized leaps to maintain group cohesion under pressure. Such findings underscore the adaptive versatility of stotting, inviting further exploration into its multifaceted functions. In the final analysis, the art of stotting epitomizes the evolutionary truth that survival in the savanna demands more than brute strength or sheer speed. It requires a sophisticated integration of form, function, and behavior. Each leap, powerful yet precise, conspicuous yet calculated, speaks to millions of years of predator-prey coevolution, where every advantage is hard-won and every signal must be credible. Through stotting, Thompson's gazelles teach us that the most effective defense can be a bold display of fitness, turning transparency into a shield and daring into deterrence. As the herd bounds away, silhouettes etched against the whitening sky, we glimpse the living dynamics of natural selection, manifested in a single magnificent action that transforms vulnerability into advantage and danger into an opportunity for triumph. In the sun-drenched expanses of the Kalahari and southern African savannas, where the heat shimmers off the parched earth and the sparse grasslands stretch toward a relentless horizon, a tiny drama of vigilance and survival unfolds on the scale of centimeters rather than kilometers. Here, the meerkat, surprisingly small, barely tipping the scales at a kilogram, has carved out a niche that belies its size, thriving amid predators as diverse as aerial eagles and stealthy jackals. The secret of this diminutive mongoose's success lies not in brute force or raw speed, but in an intricate social choreography centered on a single principle: never let down the guard. Meerkat society is built upon the sentinel system, a rotating watchtower duty in which at least one individual stands upright on a high perch, eyes flicking across the landscape, ever on the lookout for danger. It is a world governed by subtle signals, shared duties, and complex communication, in which every chirp, bark, or trill can mean the difference between feast and famine, life and death. As dawn's first light brushes the sky with pale pink and lavender, meerkats emerge from the cool sanctuaries of their underground burrows, a labyrinthine network that can extend for dozens of meters, with multiple entrances concealed by tufts of grass or the shadows of fallen logs. These burrow systems provide refuge from midday heat and nocturnal predators alike, yet they also present vulnerability. While some group members lounge in the cool tunnels, others must venture forth across the sun-baked ground to forage for tubers, beetles, small reptiles, and scorpion larvae. The balance between nourishment and safety is maintained by the sentinel, a meerkat selected by a subtle gesture, a brush of the nose, a slight tail flick, who then ascends to the nearest termite mound, rock, or vantage point that offers an unobstructed view of the horizon. In this elevated posture, the sentinel stands as still as a statue, spine erect, forepaws clasped together, scanning the sky for the telltale silhouette of an eagle or the flicker of movement across the grass that might signal a snake or jackal. The sensory adaptations of meerkats are finely tuned to this sentinel role. Their eyes, set high on flattened skulls, possess a higher density of cone cells than many other small mammals, granting them sharp visual acuity in bright light conditions. A dark ring of fur surrounds each eye, reducing glare and functioning much like the black markings used by athletes to shield their eyes from the sun's glare. Their hearing, too, is exceptional. The large conical ears can swivel independently to pick up the faintest rustle of an approaching mongoose or the low-frequency hum of distant traffic, an unexpected modern threat in fragmented habitats. Even their sense of smell is employed strategically. A sentinel may point its snout into the breeze, inhaling air currents to detect predators downwind before they come into view. These sensory gifts transform the tiny meerkat into an efficient early warning system, scanning a world 10 times its own size as though it were a living radar. When the sentinel spots a threat, the alarm is raised through a repertoire of discrete calls: sharp bark trills for aerial predators, rolling chirps for terrestrial danger, and a specialized hiccup call that warns of venomous snakes. These vocalizations are precise. Studies have shown that each call carries specific information about predator type, size, speed, and even distance, allowing the foraging group to choose the correct escape response. Upon hearing an aerial alarm, meerkats instinctively duck into the nearest burrow entrance, where they remain until the sky is clear. A ground alarm brings them back toward the sentinel's vantage point, seeking safety within the protective circle of the group. The synchronization of these responses, honed through countless generations, turns the meerkat clan into a single organism of collective defense, each individual's safety secured by the unwavering gaze of the sentry. This system of shared vigilance comes at a cost. Sentinels forego feeding during their watch, standing resolute in the sun until relieved by another group member. Yet the benefits far outweigh the sacrifices. Foraging rates among sentry-backed groups are significantly higher, as individuals can concentrate on digging for insects without the constant need to scan the horizon. This division of labor is maintained through a fluid hierarchy, in which dominant females and males often take shorter, more frequent turns on duty, while subordinate adults and older juveniles volunteer for longer stints. The altruism implied by sentinel duty is in fact underpinned by reciprocal benefits, the guarantee that every meerkat will be protected when it is its turn to feed. In this way, individual risk is shared equitably across the group, reinforcing social bonds and boosting overall fitness. Behind the scenes, the temperature extremes of the savanna exert additional pressures on meerkat behavior. During the midday heat, burrow temperatures can remain 10 degrees cooler than the surface, influencing the group's schedule of above-ground activity. Foraging and vigilance occur predominantly in the cooler hours of dawn and dusk, with the hottest parts of the day spent in shaded tunnels or the cool refuge of communal sunning chambers deeper underground. These behavioral thermoregulation strategies reduce water loss, critical for an animal that obtains much of its hydration from prey and cannot tolerate extended periods without moisture. Meerkats' kidneys are adapted for maximal water reabsorption, concentrating their urine to minimize loss. But even so, their success depends on the efficient timing of activity and rest, choreographed around their sentinel system to ensure that all protective duties are fulfilled during cooler, less stressful periods. Ecologically, meerkats exert a disproportionate influence on their environment. As they dig for insects, they aerate the soil, promoting nutrient cycling and plant growth. Their burrow systems create microhabitats for lizards, rodents, and invertebrates, expanding local biodiversity. Yet this ecosystem engineering also attracts larger predators. Monitor lizards slip into vacated tunnels to hunt dormice, while snakes exploit the same passages to pursue rodents. The meerkat sentinel, ever watchful, adapts its gaze to both the sky and the ground, ensuring that neither predator goose nor predator serpent catches the group unaware. In rare behavioral observations, meerkats have even been seen confronting cobras at tunnel entrances, using rapid impetus and group coordination to flush the snake out rather than flee. An unexpected reversal of predator-prey roles that speaks to their boldness and strategic acumen. Juvenile training further cements the meerkat's sentinel tradition through an extended period of social learning. Pups first emerge from their den at around 3 weeks of age and remain within sight of the burrow for weeks, observing adult behaviors from a safe distance. As they grow, juveniles participate in play bouts that mimic sentinel postures, standing on hind legs, scanning the horizon, while their mothers and aunts watch, issuing corrective chirps when posture wavers or attention drifts. These early lessons refine the pup's balance, strengthen the extensor muscles of their hind limbs, and instill the heightened alertness necessary for effective sentry duty. Only after several months of practice do young meerkats graduate to actual sentinel rotations, at which point they are physically and cognitively prepared to shoulder the burden of group defense. Despite the sophistication of their sentinel system, meerkats remain vulnerable to habitat fragmentation and human disturbance. Fences, roads, and agricultural expansion can interrupt sentinel rotations and reduce burrow access, exposing groups to heightened predation risk. Conservation efforts that maintain contiguous tracts of suitable habitat and minimize road mortality are critical to preserving the meerkat's intricate social structure and the ecological services it provides. In some protected reserves, researchers have even experimented with installing artificial termite mound replica perches to restore sentinel vantage points lost to land degradation, successfully boosting foraging efficiency and survival rates among local populations. In the endless cycle of life and death on the savanna, the meerkat's watchtower world stands as a testament to the power of cooperation and specialized adaptation. Each sentry perched against the sky is more than a solitary guardian. It is the living embodiment of an evolutionary contract in which vigilance is currency and life is a communal project. From the shimmering heat of midday to the cool hush of dawn, the meerkat clan weaves a tapestry of signals, postures, and strategic movements that transforms vulnerability into resilience. Through the sentinel system, these tiny mammals have erected an early warning network more complex than any static fortress. A dynamic, breathing shield that ensures eyes are always above, always watching, and always ready to sound the alarm when danger dares to approach. In their world, survival is not the triumph of an individual, but the triumph of shared vigilance, an enduring strategy that has allowed meerkats to flourish in one of the planet's most unforgiving landscapes. In the vast tapestry of the African savanna, where seasonal rains cycle through rhythms both predictable and capricious, few creatures embody the intersection of intellect, emotion, and survival as profoundly as the African elephant. As dawn's golden rays illuminate the endless horizon, a matriarch leads her herd with a measured gait, born of decades spent traversing these landscapes. The terrain beneath her massive feet, parched earth cracked by dry season heat, riverbeds strewn with bleached bones, grasslands flush with new growth, speaks to a world in constant flux. Yet for the elephants, this ever-changing stage is navigated not through instinct alone, but through the rich tapestry of memory, woven over generations, which serves as both map and guide in the quest for sustenance and safety. Elephant society is anchored by the matriarch, the oldest and often largest female in the herd. Her tenure at the helm is not a mere matter of size or strength, but of knowledge accumulated over a lifetime that can span 60 years or more. Within her mind resides the precise timing of past droughts, the exact locations of ancient waterholes now rarely filled, and the shifting boundaries of human settlements that have crept into the elephant's domain. This cognitive archive is deployed with remarkable fidelity. When the sun climbs unrelentingly and surface water vanishes from sight, the matriarch recalls a hidden spring encountered decades prior, its entrance concealed beneath a cluster of termite mounds, and guides the herd across miles of sun-scorched plains to drink again. In periods of acute water stress, her decisions can mean the difference between life and death, as calves, elderly cows, and injured bulls rely on her wisdom to find the life-giving fluid that sustains mammalian physiology and cools overheated bodies. The elephant's relationship with water is an intimate one. Their large, semi-permeable skin and extensive vasculature demand efficient thermoregulation. Without access to water for drinking, bathing, and mud wallowing, their core temperatures can rise to lethal levels. Elephants often dig for subterranean water with their powerful tusks and forefeet, creating shallow wells that fill with moisture drawn from underground aquifers. These wells, known as groundwater holes, are shared resources. After elephants excavate them, a multitude of savanna species, buffalo, antelope, birds, even small mammals, converge at these life-sustaining sites. The matriarch's memory of which sandy patches to dig, and when the water table is high enough to yield, thus benefits entire ecosystems. This behavior exemplifies a rare form of ecological engineering, where one species reshapes the land in a manner that ripples outward, influencing plant growth, predator distribution, and overall biodiversity. Navigating the savanna also requires an acute understanding of seasonal forage availability. Elephants are mixed feeders, consuming up to 150 kilograms of vegetation daily, including grasses, leaves, bark, and fruit. Over their lifetimes, matriarchs learn the phenology of key plant species, when certain acacias flower, when marula trees bear their nutritious fruit, and when specific grasses reach peak nutritional value. This phenological mapping allows the herd to follow a temporal itinerary, shifting from riverine forests during the dry season to open plains in the wet season, each move timed to coincide with optimal food quality. Calves, born only after a 22-month gestation, imprint on these migratory routes from their first weeks, learning the subtle cues in air temperature, sky color, and seasonal plant chemistry that signal it is time to embark on the next leg of the journey. Yet memory's role extends beyond resources to the navigation of danger. Elephants have been documented avoiding areas where they once encountered human hunters, steering clear of villages and roads where snares were set or gunshots echoed. They recognize the scent of poaching camps and modify their routes accordingly, sometimes crossing rivers or detouring through dense bush to minimize risk of ambush. In one recorded instance, a herd altered its established migratory corridor after a poaching attack claimed the lives of 2 juveniles. In subsequent years, despite the absence of human threat, the herd continued to avoid that tragic stretch of grassland, illustrating a lasting avoidance behavior rooted in memory and emotional association. Within the protective circle of the herd, social bonds confer both warmth and safety. Calves, with their unsteady legs and naive curiosity, are shielded at all times by the adults, frontline defense against opportunistic predators. When lions or hyenas approach, the herd's formation tightens into a defensive semicircle, the adults' massive bodies and interlocking tusks presenting a wall too formidable for most predators to breach. Even an adult bull, often solitary or in bachelor groups, will sometimes rejoin a matriarchal herd in times of crisis, drawn by the communal instinct that offers greater safety in numbers. This solidarity extends beyond immediate kin. Female elephants remain within their natal herds for life, fostering complex networks of aunt-niece and grandmother-granddaughter relationships that reinforce social cohesion and collective defense strategies across generations. Emotional resonance threads through elephant memory and sociality. Elephants exhibit signs of grief and mourning, returning to the bones of long-dead companions and gently touching tusks to remains, as though commemorating shared history. Such behaviors underscore the depth of their memory, not merely as a cognitive map of the landscape, but as an emotional tapestry connecting individuals across time. This emotional memory informs practical survival choices. Older females are more likely to volunteer as allomothers, individuals who assist in infant care, sharing the burdens of vigilant defense and enabling mothers to forage and rest. These cooperative care networks enhance calf survival rates, reinforcing the matriarch's position as both leader and custodian of the herd's future. Sensory adaptations complement the elephant's mnemonic prowess. Infrasound communication allows herds to exchange low-frequency calls that travel several kilometers through the ground and air, transmitting information about water sources, danger, or group location even when visibility is nil. Young calves, whose ears lie close to the ground, detect these vibrations through sensitive mechanoreceptors, tuning into the herd's collective wisdom before their eyes can discern distant objects. When drought shrinks waterholes and scatters vegetation, elephants use infrasound to coordinate widely dispersed individuals, converging on reliable springs before competition for limited resources intensifies. Such long-range coordination, guided by memory and sound, represents one of nature's most advanced communal survival systems. Yet for all their intelligence and social complexity, elephants face challenges that outstrip even the most seasoned matriarch's memory. Rapid habitat loss, driven by human expansion, chokes ancient migratory corridors with fences and roads, severing the pathways elephants have followed for centuries. Poaching, despite extensive conservation efforts, continues to erode populations and deplete the ranks of older females whose knowledge is irreplaceable. The loss of just a few matriarchs can render a herd directionless, leading to increased calf mortality, as younger, inexperienced leaders struggle to find water and navigate predation hotspots. In one documented case, a herd without a mature matriarch wandered into a farming village in search of crops, resulting in human-elephant conflict that ended disastrously for both sides. This tragic outcome underscores the vital role of memory keepers in guiding elephants through an increasingly fragmented world. Conservation strategies now recognize the elephant's cognitive and social needs, prioritizing the protection of older females and the maintenance of habitat connectivity. Wildlife corridors modeled on historic migratory routes and community-based conservation programs aim to preserve the matriarch's domain and ensure that memory's weapon remains sharp and accessible. Technological innovations, from GPS tracking to acoustic monitoring of infrasound, help researchers map herds' movements and anticipate their needs. But the most crucial factor remains the elephant's own knowledge, passed down through generations via the matriarch's leadership. In the final analysis, the African elephant's greatest weapon is neither its tusks nor its size, but the intricate web of memory and social bonds that guides each herd through a world fraught with danger and change. The matriarch's recall of water sources and safe routes, her emotional understanding of loss, and her stewardship of communal traditions converge to create a survival strategy unmatched in the animal kingdom. As the sun dips beneath the horizon and long shadows stretch across the savanna, the herd gathers once more at a hidden spring, calves lapping eagerly, adults bathing in the cool water, and the matriarch standing sentinel. Her gaze both backward into the past and forward into an uncertain future, embodying the wisdom that has sustained her kind for millennia. As the sun dips below the horizon and the African savanna slips into the violet embrace of twilight, a subtle but profound transformation begins. The once scorching plains cool rapidly, shadows lengthen into impenetrable corridors, and a host of hidden actors emerge from the subterranean world to claim the darkness as their sanctuary. Among the most remarkable of these nocturnal specialists is the spring hare, a slender rabbit-sized rodent equipped with powerful hind limbs that propel it into bounding leaps reminiscent of its distant kangaroo cousins. Yet for all their outward familiarity, spring hares possess an array of survival strategies so finely tuned to the cover of night that their very existence hinges on remaining unseen, unheard, and utterly invisible to the savanna's daytime predators. Emerging from burrow entrances nestled beneath termite mounds, spring hares slip into the cool night air with cautious grace. Their tunnels, excavated with dexterous forepaws, extend for as much as 30 meters, forming a labyrinth of chambers that serve as both nursery and refuge. These subterranean complexes maintain stable temperatures, 10 to 15 degrees cooler than the surface by day and warmer by night, creating a microclimate that shields vulnerable spring hares from the extremes of desert heat and the chill of early morning. The architecture of the tunnel itself reveals ecological intelligence. Entrances face away from prevailing winds, minimizing scent trails that aerial predators like barn owls could follow, while smooth rounded walls prevent claws or talons from gaining purchase in pursuit of a fleeing prey. As darkness deepens, spring hares depart their burrows in short bursts of activity, foraging for tubers, bulbs and succulent roots with incisors that continually grow to counter the relentless wear of gnawing through tough vegetation. Their diet, rich in underground plant parts, provides both moisture and nutrients, allowing them to avoid the open waterholes where lions, hyenas and leopards lie in wait. Ingesting water-laden roots is more than convenience. It is a vital adaptation for an animal whose renal system is optimized for intense water conservation. With highly efficient kidneys that produce a paste-like urine, spring hares minimize water loss, ensuring that each night's forage yields both caloric and hydric sustenance necessary for maintaining muscle power and thermoregulation. Movement under the stars is a study in economical propulsion. When threatened, spring hares engage their extraordinary hind limb musculature, each leap powered by elastic tendons, storing and releasing energy with an efficiency that rivals elite athletes. Bounding at speeds up to 40 kilometers per hour, they cover distances of 2 to 3 meters per leap, zigzagging across open ground in patterns that disrupt a predator's ability to predict trajectory. Unlike diurnal prey whose flight leaves a straight-line spoor, the spring hare's unpredictable bouncing confounds trackers. Footprints appear as irregular dots rather than continuous trails, forcing a pursuing jackal or serval to expend precious energy deciphering which dots to follow. Sensory adaptations underscore the spring hare's nocturnal mastery. Their large dark eyes are rich in rod photoreceptors, granting enhanced low-light vision, while a pronounced tapetum lucidum reflects residual light, amplifying images in near darkness. Long whiskers above the snout and along the forelimbs probe the air and ground, detecting subtle changes in texture and airflow that hint at approaching danger. When an owl's wing beats stir the ether or a snake's slither disturbs the ground, the spring hare's whiskers and sensitive vibrissae transmit minute vibrations to mechanoreceptors, triggering instantaneous retreat to the nearest tunnel entrance. In this way, spring hares navigate a world of sound and sensation as much as sight, mapping threats in 3 dimensions before a predator closes the gap. Yet survival through invisibility extends beyond individual behavior to a rhythm dictated by lunar cycles. On moonlit nights, when silver light bathes the landscape, spring hares curtail their foraging, preferring the half-shadowed veil of new or waning moons. This lunar phasing reduces silhouette exposure against the bright ground, lowering the risk of detection by nocturnal raptors whose vision excels under starlight. Conversely, during the darkest nights, spring hares venture farther from their burrows, exploiting the cloak of near pitch black to expand their feeding range. This cyclical adjustment in activity demonstrates a temporal sophistication seldom attributed to rodents, a behavior finely attuned to both celestial rhythms and predator sensory capabilities. Predator-prey interactions in the spring hare's nocturnal domain reveal rare and extraordinary behaviors. Some barn owls have been observed perching near prominent termite mounds, not only to hunt spring hares, but also to modulate their own calls based on moonlight levels, using softer, low-frequency hoots that carry farther in dense air, yet betray less of their position. Meanwhile, spring hares sometimes engage in deceptive freezes, flattening themselves against the ground with hind legs tucked beneath the body and forelimbs folded, reducing their profile to a low-contrast patch that blends seamlessly with the night soil. This combination of flight and freeze tactics exploits predators' reliance on motion detection. When the prey stops moving, the attack often stalls. Furthermore, spring hares contribute to the savanna ecosystem in surprising ways. Their burrow systems aerate compacted soils, facilitating water infiltration and seed germination, while discarded plant remains from foraging enrich nutrient cycles. In some regions, these burrow networks create refuges for other small animals, dormice, small reptiles, and even invertebrates, forming microhabitats that increase local biodiversity. Ironically, it is through their unseen, subterranean engineering that spring hares shape the very environment they must remain invisible within, a testament to their dual role as ecosystem architects and master survivors. The reproductive strategy of spring hares also reflects their nocturnal niche. Breeding occurs year-round but peaks after rains, when vegetation surges and burrow entrances proliferate under softer soils. Females give birth to litters of 1 to 3 precocial young in deep chamber nests lined with grass, where the pups remain almost entirely underground for the first 3 weeks of life. During this vulnerable period, males and non-breeding females assume sentinel roles at burrow entrances, emitting faint grunts that signal all is clear before the mother reclaims her pups for nursing. Such cooperative care underscores the species' social flexibility, a contrast to the solitary image often associated with small rodents, and highlights how complex social behaviors can arise even in mammals that operate predominantly in the dark. Thermoregulation during nocturnal activity presents its own challenges. While the night brings relief from daytime heat, temperatures can plummet rapidly, risking hypothermia in small-bodied mammals with high surface area to volume ratios. Spring hares counter this by tucking their limbs close to the body during pauses, conserving heat through reduced airflow and employing a specialized fur underlayer of dense, insulating hairs. Their burrow chambers serve not only as refuge from predators, but also as thermal havens, where residual earth warmth from the day's heat lingers, offering a stable environment in which resting individuals can minimize metabolic expenditure before the next foraging foray. As dawn approaches and the horizon flushes with the first glimmers of light, spring hares retreat into their tunnels once more, slipping underground before diurnal predators, baboons, raptors, and snakes claim the surface. Their nighttime odyssey folding back into the earth, they leave behind a landscape barely altered by their passing. Only in the subtle disturbances of loose soil and the emptied cavities of roots does one glimpse evidence of their nocturnal empire. In a realm where visibility equates to vulnerability, spring hares have perfected the art of living between worlds, dwelling underground by day, bounding under stars by night, and emerging only when the savanna's greatest hunters are blind to their presence. In the end, the spring hare's nocturnal tenure is a testament to the power of invisibility as a survival strategy. Their combination of physiological adaptations, behavioral finesse, and ecological engineering reveals a species that thrives not through dominance of the open plains, but through mastery of shadow and subterranean refuge. As the sun ascends and the world of daylight predators reclaims the savanna, the spring hare's nightly kingdom dissolves into silence, yet the legacy of its hidden lives endures in the subtle, transformative imprints left upon the earth. In this dance of darkness and earth, the spring hare illustrates the profound truth that sometimes the greatest strength lies not in confrontation, but in remaining unseen.